Welcome to the next video for Module 3B of MCT 450 Advanced Mechanics. In this video, we will get into the details behind beam stresses. When a transverse load is applied to a beam, it affects various locations within the beam in different ways. Imagine a downward force on a simply supported beam, as in the one shown. The outside of the beam at the point where the load is applied is put into compression. The outside surface opposite the load is put into tension. Within the beam, variable stresses are developed. There is no bending stress at the longitudinal axis of the beam. This is why the axis is also known as the neutral axis. As you move from the neutral axis, where the stress is zero, toward either outside surface, the stress gradually increases. The magnitudes of the stress at top and bottom are equal but opposite signs. This stress distribution is the reason that the formula for bending stress is M times C over I. Remember, variable C is the distance from the neutral axis, which also coincides in most cases with the centroid of the 2D cross-section to either outside surface. The stress is maximum at this point on the beam. Recall the bending stress formula shown here. Note that M times Y divided by I is equivalent to M times C divided by I. The variable Y is the distance from the neutral axis to the outside surface of the beam. The variable C is the distance from the centroid of the 2D beam cross-section to the outside surface of the beam. For straight beams with consistent cross-sections, these two variables are equal. At times, you may see a reference to the section modulus. This term and method are often used by structural engineers. For structural engineering, the formula M divided by Z is used for bending stress, but Z is simply the moment of inertia divided by the centroidal distance. Again, this is simply MC over I and just another inversion of the formula. Curved beams are quite a different matter and usually require more complex analysis. An example of a curved beam would be a lifting hook that connects to a load. Because of the curvature of the beam, the neutral axis and the centroidal axis are no longer coincident like they are for typical straight beams. Thus, this changes the resulting stress profile from the inside of the hook to the outside of the hook. The curvature to radius ratio tells you how to proceed with the analysis. If the ratio is less than or equal to 0.1, you can analyze the hook as if it were a straight beam and simply multiply the stress results by 1.1. However, most hooks do not meet this criteria and must be evaluated by other methods. The Winkler-Bach method provides a reasonable method to approximate the stress in curved beams. Whenever this method is used, you should always verify the results with FEA. To use this method requires a table of correction factors, which is available through various sources. The key to using the tables is to define the cross-section shape of the hook. Shown here is an example using a square cross-section hook. Using the formulas provided, you can calculate the inner and outer hoop stresses on the hook. Use whichever one is higher to define your factor of safety. In this course, you will not be asked to analyze any curved beams using these methods. Recall that whenever a beam is transversely loaded, it results in both bending and shear stresses. The bending stress is usually the higher magnitude of the two stresses. The bending stress and the shear stress tend to behave in an opposite manner. Recall that the bending stress is highest at the point furthest from the neutral axis. Shear stress is zero at the outside surface and maximum at the neutral axis. Students often struggle with this concept. The image shown provides a graphical representation of the internal stress distribution for bending stresses here on the left and shear stresses here on the right. Note where the maximums occur. While the bending stress formula is consistent for any standard beam cross-section, the transverse shear stress formula is cross-section dependent. It is based on the variable Q, which is known as the first area of moment. This variable is an integral of the area of the cross-section and thus changes based on the shape. In this course, you will not be required to calculate this value. Rather, you will look up derived formulas from tables. This slide demonstrates how to derive Q and subsequently the transverse shear stress formula for a rectangular cross-section. Based on the simplicity of the cross-section being considered, it is not a difficult derivation. More complex shapes involve more complex solutions. Here are the formulas for transverse shear stress provided in our textbook. You should take note of these and keep them handy for homework and exams. That's it for this video. Thanks for watching.